Değerli katılımcılar, değerli dostlar, sosyal medya platformları üzerinden bizi izleyen ülkemizin bilim dostu, bilgisever, güzel insanları. TÜBİTAK Temel Bilimler Araştırma Enstitüsü, heyecan verici bilimsel eylemleriyle dünyadaki temel bilim alanlarındaki üst düzey ve yenilikçi bilgileri ülkemizin bilim ve eğitim camiasına aktarmaya devam etmektedir. Bugün matematiksel fizik ve uygulamalı matematik seminer serimiz kapsamında bir araya gelmiş bulunmaktayız. Bu vesileyle ben de hepinizi saygı ve sevgiyle selamlıyorum. Bugün son derece derin ve heyecan verici bir konuyu, kuantumu, gravitasyonu ve geometriyi konuşacağız. Bu kapsamda konunun dünyaca ünlü baba isimlerinden son derece değerli bir bilim insanı, ABD Milli Bilimler Akademisi üyesi, Penn State Gravitasyon ve Kozmos Enstitüsü'nden Profesör Doktor Abhay Ashtekar bizim konuşmacımızdır. Profesör Ashtekar, gravitasyon, geometri ve kuantum başlıklı bir konuşma yapacaktır. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear Professor Abhay Ashtekar, dear participants, dear colleagues and friends, a very warm hello everyone and welcome. Welcome to the inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences. We organize these seminars for national and international audiences, relying on the unifying feature of science for humanity and with the participation of distinguished scientists and great speakers of the world. It is now my pleasure to inform you that this evening we have another wonderful episode of our mathematical physics and applied mathematics seminar series. And I have the honor of introducing you very special speaker, a wonderful person, distinguished physicist and world-class expert in the field, Professor Abhay Ashtekar from the Penn State Institute for Gravitation and Cosmos. He's going to give a great talk entitled Gravity, Geometry, and the Quantum. Abhay Ashtekar is an even pure professor of physics, holder of the Eberly Chair in Physics, and the founding director emeritus of the Institute for Gravitation and the Cosmos at Penn State. Before joining Penn State, he was the Erasmus Franklin Holden Professor of Physics at Syracuse University and Professore Chair de Gravitation at Université de Paris 6. Ashtekar is a member of the US National Academy of Sciences and the winner of the Einstein Prize of the American Physical Society, given biannually for all outstanding contributions to gravitational science. He is also one of only 51 honorary fellows of the Indian Academy of Sciences, drawn from the community of scientists living outside of India. He was awarded the Senior Research Award by the Alexander von Humboldt Foundation and held the Kramer's Visiting Chair in Theoretical Physics at the University of Utrecht, Netherlands, a Senior Visiting Fellowship of the British Science and Engineering Research Council, and the Sir Raman Chair of the Indian Academy of Science. He was also awarded Dr. Rerum Naturalism Honoris Causa by the Friedrich Schiller University, Jena, Germany, in 2005, and the Université d'Aix-Marseille, France, in 2010. He is a past president of the International Society for General Relativity and Gravitation, and the past chair of the Division of Gravitational Physics of the American Physical Society. As the founding director, he led the Institute for Gravitation and the Cosmos from 1992 to 2021, that is 28 years. With this, I want to invite Professor Abhay Ashtekar to the stage to begin his talk. Abhay, good afternoon. We are very honored to have you with us. Please come and begin your talk.
Okay, I'll share the screen now. While the screen is coming up, I should say that over the last couple of years, I've been enjoying enormously the poetry of Yunus Emre, and through that, some exposure to the Turkish words. So I was happy to hear the Turkish welcome speech that we just heard just now. Okay. All right. So this is the topic of my talk today: gravity, geometry, and the quantum. And the organization of the talk is going to be as following. It's not addressed to experts. It is addressed to a general audience. And so I'll begin first with a conceptual setting of what is quantum gravity, why is the problem difficult, and then a brief introduction to loop quantum gravity, one of the leading approaches to quantum gravity as a whole. In the third part, I will talk about an illustrative example, which is to the early universe. Because we don't have enough time, I will not be able to talk about the applications to black holes, information loss, etc. But if there are questions, I'll be happy to answer them. Also, there is a lot of very beautiful and very deep mathematical work that many of my colleagues have done. And unfortunately, again, I will not be able to cover it all. But there is a recent short review about a few months ago, actually, not a year ago, that appeared. It's on the archives with Eugenio Bianchi, which gives us, summarizes the status up here. Okay, so let's begin with the first part, which is the conceptual setting. Now, Einstein himself, as you know, the founder of general relativity, it is well known that for him, quantum mechanics was not a complete theory. And so his resistance to accept quantum mechanics as a fundamental theory is quite well known. However, Einstein did have deep respect for quantum mechanics and was the first to raise the problem of unifying general relativity with quantum theory. And here is a quote from the paper in which actually he introduced the gravitational waves for the first time. Nevertheless, due to inner atomic movement of electrons, atoms would have to radiate not only electromagnetic, but also gravitational energy, if only in tiny amounts. So this is the prediction of the classical theory. And then he says, as it is hardly true in nature, because if the atoms were radiating so much, then they would be unstable. Quantum theory would have to modify not only the Maxwellian electrodynamics, but also the new theory of gravitation, namely general relativity. So this was in 1916, is more than a century now, and why is the problem still open? Well, physics advanced tremendously over the last century, but the problem of unification of general relativity and quantum physics is still open. Usually people say that, well, the problem is that our technology is not sufficiently advanced to have direct experimental data, which shall have ramifications of the quantum nature of gravity. But this is not really a good answer, because if this was the case, then this should be a kind of a theorist heaven, right? If this was the only difficulty, then we should be able to churn out a new theory every day. But we don't have a single coherent, consistent, complete theory, even 100 years later. So this cannot be the answer. So then the real answer from point of view of loop quantum gravity that I found it a long time ago is really the following. That the real reason is that in general relativity, gravity is encoded in space-time geometry. The most spectacular prediction, for example, the Big Bang, the black holes, and the gravitational waves, they emerge from encoding of this gravitational field into geometry. So this suggests that if you want to have a quantum theory of gravity, then geometry itself must become quantum mechanical. But if the geometry is quantum mechanical, how do you do physics? If you don't have a classical space-time in the background, how are you going to do physics? So that is kind of the big open problem, and has been an open problem for the longest time. We need really brand new paradigm. We need new concepts and new mathematical tools. We really need a completely new setting. And we learn how to lift the anchor that had tied us to a background classical space-time, and then sail the open seas to explore the world without this classical background only relatively recently. And now there are several voyages in progress. There are several approaches, starting from non-commutative gravity, twistors, Regge calculus, Euclidean quantum gravity, Hosover-Lifshitz, causal sets, asymptotic safety, causal dynamical triangulations, ADF-CFT conjecture in string theory, and loop quantum gravity. But because there is no direct experimental checks, approaches tend to be driven by intellectual prejudices of what are the core issues and what will take care of itself once these issues are addressed. So this is the status, but this sounds very strange because we think it is science, and science should not be really dependent on one's intellectual prejudices about what the core issues are and what will take care of itself. Shouldn't it be much more objective? And here there is a very beautiful quote from C.N. Yang, which sort of sets the whole issue in a really beautiful and correct perspective, in my view. He says that taste and style have so much to do in physics may sound strange at first, since physics is supposed to deal objectively with the physical universe. But the physical universe has structure, and one's perception of this structure, one's partiality towards some of its characteristics and aversion towards others, are precisely the elements that make up one's own taste. Thus, it is not surprising that taste and style are so important in scientific research. And so we have to keep this in mind. Of course, ultimately, the difference between, say, arts or something, or other disciplines and science is that ultimately there are experiments, and experiments will decide which of these ideas are correct and which of these ideas are not, as they have done throughout the history over the last 200-300 years. Now, here is an example, just one example of illustration of taste and style. And I'm going to use two leading approaches, string theory and loop quantum gravity, to illustrate it. String theory was developed by high energy theorists, and therefore a theme that is central was unification of all interaction. And therefore they introduced supersymmetry, they introduced higher dimensional spacetimes, they introduced a negative cosmological constant at the foundation of the theory itself. And then there are extended objects rather than point particles, which is supposed to introduce a natural ultraviolet cutoff to cure the ultraviolet divergences of standard quantum field theory. But loop quantum gravity, by the other hand, has a different set of aesthetics and values, and therefore intellectual prejudices. It was developed by general relativists, and therefore non-perturbability methods and background independence. That is to say, the idea that we really have a single space-time which encodes gravitational field. It is not supposed to be a flat space-time on which there is a little bit of perturbation. There's only one space-time, and that space-time geometry is physical. There is no background kinematical space-time geometry. That has been a fundamental principle in loop quantum gravity. And therefore, it is based on quantum Riemannian geometry. Just like general relativity is based on Riemannian geometry, loop quantum gravity is based on a quantum version of that. And because of that, quantum geometry itself is quantum mechanical, and therefore there is an ultraviolet built-in cutoff. So there are common elements, but there are also very, very big differences. Initially, there was a great hope that this would provide unification of all interactions. This has not been borne out so far. Supersymmetry, there has been great search at CERN, has not been found. There are higher dimensions. We don't have any evidence of it. And the cosmological constant is really positive and not negative. And therefore, the current status is the following. And this I have taken straight from the Institute of Advanced Studies website. And this article is by a journalist in residence who interviewed various experts in the Institute. And the article is called The Strange Second Life of String Theory. String theory so far, it says, has failed to live up to its promise as a way to unite gravity and quantum mechanics. At the same time, it has blossomed into one of the most useful sets of tools in science. Loop quantum gravity, on the other hand, the focus continues to be on the long-standing problems of quantum gravity itself. The problem of time. If you don't have a background space-time, what do you mean by time? What do you mean by evolution? General relativity predicts that there are singularities, the Big Bang singularity, the black hole singularities. Can they be tamed? Can there be pre-inflationary dynamics of loop quantum gravity, of quantum gravity epoch? Can that pre-inflationary dynamics have effects that can be observed in the anomalies of the cosmic microwave background? And then, can we get graviton propagator and endpoint functions in a theory without a background space-time? So these are the issues that loop quantum gravity has focused on. So this is the first part of the talk that is over. Now let me begin with the second part, which has to do with introduction to loop quantum gravity per se. So we began with Einstein's outrage. We begin with general relativity. And general relativity began with this Einstein's really outrageous idea that gravity is not a force. For 300 years since Newton, we all thought that the gravity was a force. And Einstein said that no, it's not a force, but it's a manifestation of the curvature of space-time. Space-time is flat in absence of massive bodies. Massive bodies curve it, and gravity is a manifestation of that. And therefore, general relativity needed a new syntax, a new basic framework to describe physics, a basic language to describe physics. And that syntax was provided by Riemannian geometry, branch of mathematics. Loop quantum gravity. In loop quantum gravity, the view is that since geometry is a physical entity like matter, it also should have atomic structure. And quantum gravity, therefore, needs a new syntax. And the new syntax is going to be has been provided by quantum Riemannian geometry. So I'll tell you a little bit about this new syntax. Now, to probe this atomic structure of geometry, we need non-perturbative approach. We cannot have a classical flat space-time metric and on that a little perturbations because continuum is only an approximation. We need the fundamental atomic structure itself. And the metric, space-time metric, is to emerge on coarse graining of this atomic structure. So in this spirit, Dirac, Bergman, and Wheeler and others introduced what they call quantum geometry dynamics using the Hamiltonian approach. And Misner, Hawking, and others introduced a sum over histories approach along Feynman path integrals. And both these approaches use the space-time metric as a fundamental dynamical variable following a general relativity treatment of Einstein's. But it turns out that if you use that, then the action which is used in the path integrals and the equations of motion, which are used in the Hamiltonian framework, they are highly non-polynomial in the metric and the conjugate momentum. And for example, in this case, we can take a three-dimensional space-like surface and look at the metric on this surface. That is a configuration variable of general relativity. And then just like for particle, the position is a configuration variable. Where is the particle at an instant of time? So where is the space-time geometry at an instant of time? That is really a three-dimensional metric. And its conjugate momentum is PAB. And that is, in differential geometry language, the extrinsic curvature at that instant of time. And the Hamiltonian density of general relativity is given by the determinant to the 1/2 times scalar of the metric, determinant of the metric to the 1/2 times scalar curvature, and again determinant to the metric to the 1/2. Now, these quantities are highly polynomial, non-polynomial in the metric variable. Because they are non-polynomial, in quantum theory, hard field theoretical issues would not be dealt with because we know how to regularize products of operators, but these are non-polynomial functions, and we did not know how to regularize them. And therefore, in both the Hamiltonian approach and in the sum over histories approach, the treatments have been formal. In the sum over histories approach, the measure of the space of paths we don't know. In the Hamiltonian approach, the rigorous Hamiltonian operator is not known. And both these things change dramatically in loop quantum gravity. The key ideas is really a shift of paradigm already in the classical theory. And this shift is really going from the metric to a vector potential as in gauge theories. And for a contemporary perspective and new results and direction, there is an article that appeared again a few months ago with Varadarajan that you can see that. So the idea is to start with a gauge theory, and that gauge theory has no background metric. Usually when we take gauge theories like electrodynamics or Yang-Mills theory, there's a flat or curved background metric. Now there is no background metric. But we can still talk about a phase space, and the phase space is a vector potential, and this is supposed to be an SU2 gauge theory. Therefore, it's a matrix valued vector potential. If you like, this little I is a Lie algebra valued index, and it's canonical conjugate electric field. The phase space can be defined without reference to any background metric. Even the symplectic structure and the Poisson brackets can be defined without any reference to any background metric. But we need to do dynamics. And so therefore, we would like to know what is the Hamiltonian density. It turns out that if you do not have a background metric, then there are very few expressions which you can write down using just the vector potential and its canonical conjugate electric field. Mathematically, the connection and this electric field is really two-form. So we can look at this Lie algebra valued two-form and Lie algebra valued connection. And it turns out that all the simple expressions actually have direct meaning in general relativity, but the Hamiltonian density is now just given by E times F, and the indices are internal indices of the SU2 indices. The Lie algebra indices are tied down with the structure constants of SU2. So here is a very simple expression. It is quadratic in the momenta, and its F is just at most quadratic in the electric field. In the Yang-Mills, in Maxwell theory, F will just be given by the curl of A. But in Yang-Mills theory, there is also there is an internal index, and therefore I got an internal index here. So in Yang-Mills theory, FAB has an internal index, and that is just given by FAB of I will be given by 2 times dA of AAB I, like in Maxwell theory. But then there is another term, which is IJK, AAJ, ABK. So I got a quadratic term up here. And therefore, this is at most quadratic in the vector potential and quadratic in electric field, but it's very low order polynomials. And therefore, we can take this and we can go to quantum theory. But already in the classical theory, the metric is now, there's no metric here. So how is Riemannian geometry supposed to arise? So the metric is now a derived quantity. What you do is that this E in Yang-Mills theory is electric field. But really what you have is I takes values 1, 2, 3. Therefore, EAI is really a triplet of vectors. So you just declare this triplet to be an orthonormal triad. If you just declare 3 vectors as being orthonormal triad, then that gives you immediately a metric, because we're saying that these are 3 vectors which are orthonormal, and so we can contract them and get the metric up here. And the Riemannian geometry thus is now emergent. It emerged from this gauge theory, and it emerged from this background independent gauge theory. And the gauge theory itself doesn't know anything about lengths, about geodesics, about areas, etc. It's just a background independent gauge theory. It's not a Yang-Mills theory in the usual way, because dynamics is very, very different. But from that gauge theory, the geometry emerges, and then we can talk about the geometrical concepts. In the metric picture, the Wilson lines of this vector potential, they parallel, so they enable you to parallel transport. So if you give me a curve, and if you give me a spinner at this point, which is a kind of a vector with a flag, then this vector potential enables me to parallel transport it to another point, the spinner up here. So that is the interpretation of this. And the interpretation of this is that they are just orthonormal tribes. This emphasis on the gauge theory variables bring general relativity close to other basic interactions. There is a confluence of ideas from Penrose's spin networks, twistor theory, and Newman and Blavatsky's self-global gravity, Dirac's theory of constraint systems, and Feynman path integrals, and of course, gauge theories themselves. Now, there is a huge literature on loop quantum gravity. There are tens of thousands of papers. So obviously, I'm not going to cover everything. I'm just going to give you a flavor of this loop quantum gravity. So this transition in classical theory from metrics to connections or to vector potentials, now that gives us a completely new tools in quantum theory. Namely, these Wilson lines, path order exponential of A dot dl, which enables you to parallel propagate objects. So for example, in QCD, it is quarks which are parallel propagated from one thing to another by this vector potential A. In general relativity, it is a spinors. So this you give a spinner at this point, and the gravitational A parallel part transport the spinner and gives me a spinner at another point up here. So the Wilson lines are a new objects which became available because of thinking about these connections. And then you can also take these electric fields and you can take their fluxes. You can take a Lie algebra valued test field F. You can contract this and then you can integrate. And these Wilson lines and the electric fluxes, they are the basic variables. They generate a certain Poisson algebra that knows nothing about the sort of metric or anything like that, or any background fields up there. And these are operated. These are then, they form a certain, you go to quantum theory, you use a Poisson algebra, you go to quantum theory, make a quantum algebra, like the Heisenberg algebra, which is generated by Q and P. Now there is unforeseen deep mathematical results that the background independence, the fact that we have no background fields, we have mathematically diffeomorphism covariance, that guarantees that this A admits a unique representation of operators on a Hilbert space subject to standard regularity conditions. And that representation is well controlled. Infinite dimensional issues are fully controlled, where the states are square integral function on the space of these connections. And there is a regular normalized Borel measures on this space of connections. There are no background fields such as a metric, only a manifold in the background, and we have got diffeomorphism covariance. As we will see, this Riemannian geometry emerges from this framework. The quantum geometry, the quantum nature of geometry, atoms of geometry, they emerge from this framework. It turns out that because we have no background fields, one would think that life is very difficult. Yes, in a sense, it is conceptually difficult because we are not used to thinking in terms of metric independent, background independent concepts. But it also simplifies technically very much analysis because you've got a huge symmetry group up here. And therefore, we can construct this rigorous framework. And this was systematically developed by a very large number of people starting already in the 90s, and this development still continues. So what is the quantum nature of geometry? Well, the fundamental excitations of geometry are given by Wilson lines. So they are one-dimensional, they are polymer-like. And the continuum arises only on coarse graining. So to give you an example, look at this shirt that I am wearing. And this shirt, really for all practical purposes, it looks like a continuum, which is two-dimensional. But of course, you just take a magnifying glass and look and you find that it is woven by one-dimensional threads, like these one-dimensional threads. But these one-dimensional threads are tightly woven that it gives you a picture of a continuum. And that is what is happening in the real space, real geometry up here, that fundamentally its excitations are one-dimensional, but approximation gives you a continuum three-dimensional picture up here. So here is an example. I got this one-dimensional excitations coming up. They impinge on some surface, which is a two-sphere here. This was really supposed to be a black hole horizon. And at each intersection, it deposits on the surface a quantum of area. But because there are so many excitations which pierce the surface, we get a huge macroscopic quantum of total area is huge macroscopic object up here. So these fibers, the one-dimensional polymer-like excitations, are really this, they constitute a graph. And this graph actually carries some labels. Links carry a spin label, and vertices have what is called as intertwiners of SU2, which basically have these labels associated with incoming representations of SU2 and outgoing representations of SU2, and the intertwiners tie them up. So spin networks is a convenient basis of this kind, given by graphs with links which are labeled and nodes which are labeled up here. And this basis diagonalizes geometrical operators like the areas, volumes, lengths, and so on. At each node up here, you have got a chunk of space. If you like, it's a quantum of space is residing here. And each of these fibers carries quantum area. As soon as it intersects any surface, it deposits on that surface a quantum of area. So each label limb deposits a quantum of area on any surface it intersects. So it's really a quantum mechanical description, and the classical geometry arises from it on coarse graining. There are well-defined geometrical operators like areas of surfaces, volumes of regions, and so on. And these have discrete spectra. So that is really quantization. They have discrete spectra. Eigenvalues are discrete. So it is a little like what happened in atomic physics. Classically, the energy, the total angular momentum, and the z component of the angular momentum of the electron, they were all continuous variables in classical physics. But quantum mechanically, in the hydrogen atom, all of them become quantized. The spectra here become quantized. In the same way here, things become quantized. And as a result, it turns out that there is actually a very interesting and powerful thing that plays a big role, which is called the area gap. So you are, of course, if you are given a surface and there is no, if you're given a surface and nothing intersects it, its area will be zero. If there's just one intersection and I'm depositing just one quantum of area, then I get some finite answer. But between the zero and this finite answer, this one quantum of area, there's a gap, and that is called the area gap. And that area gap is about 5.17 times Planck length squared. And that plays a fundamental role. That's a microscopic parameter of the theory that sets scales for new macroscopic phenomena. For example, the curvature of space-time acquires a maximum value, and that maximum and the density of matter acquires a maximum value, and that value goes as some constant divided by 1 upon cube of this area gap. So there is a new microscopic parameter has come into existence, and as a result, that has qualitative behavior changes. For example, near the Big Bang or inside the black hole, the curvature doesn't become infinite because there is a maximum value up here. So this is the general picture. And now we can go and ask, there have been some long-standing issues of quantum gravity, and now how are they resolved? So first of all, one issue is, how do we do physics if there is no space-time metric in the background to anchor it? If only what you have is only probability distribution of various geometries. What is time, and how do you speak of dynamics and happenings? Are the strong curvature singularities of general relativity naturally resolved by quantum gravity? This was the hope since the 60s by people like John Wheeler. And all the ultraviolet divergences of quantum theory, quantum field theory, naturally resolved in quantum gravity. Now, the answers in loop quantum gravity are as follows. So first question, how do you do physics if there is no space-time to anchor it? Well, matter fields and geometry are both quantum mechanical at birth, and quantum fields propagate on the state of quantum geometry. And this state provides probability amplitude for the metric to be this, that, and the other. And the quantum fields then see all this probability distribution. Let me give an example of electrons in a laser beam. So the laser beam is supposed to be like the quantum space-time, in our case, that's the analogy. The laser beam has a quantum electromagnetic field, but it's sharply peaked at a classical field. And if there is an electron in that beam, then to the first order, it only sees this peak, the classical field. But then, of course, it also sees the quantum fluctuations up here. So the same thing happens. If you have a sharply fit quantum geometry, then the matter fields will see to first order the classical geometry on which it is peaked. But then it can also sense the fluctuations of this quantum geometry if you probe more deeply. What is time and how do you speak of dynamics? Well, a matter field can serve as a relational clock with respect to which other fields evolve. For example, in cosmology, you may, for example, have a scalar field as a matter field, and you can ask the question like, if in fact the value of the scalar field was phi equal to phi 0, and at that time, the matter density, the anisotropies of the universe, etc., had these values, what are the values of the matter fields of the matter density, curvature, anisotropies when the scalar field has some other value? So the scalar field is serving, it's one of the dynamical variables, but we've chosen it to represent the clock, and therefore what you have is a relational dynamics. What about happening? So here is one of those spin networks, and here is time evolving. And as it evolves, it traces out what is called as a 2 complex. But then occasionally a new vertex is created, a new quantum volume is created. That is what happens in the expanding universe. And when that is created, then the statement is that something happened. And then therefore over here, I got some spin network state, and here I got a spin network state with an additional vertex up here that came up. And therefore I got a transition amplitude from going from here to here that captures this happening. Are the strong curvature singularities of general relativity naturally resolved in quantum gravity? In all cosmological and black hole models considered so far, space-like strong curvature singularities are attained by loop quantum gravity. And in cosmology, also the other things which are slightly more general, the big rip and the sudden death kind of singularities. Are the ultraviolet divergences of quantum field theory naturally resolved? Here, the results are not definitive, but there are concrete results due to Thomas Tiemann on the regularity of the matter Hamiltonian in loop quantum gravity. And again, the Hamiltonians are tamed, are regularized because of the quantum nature of geometry itself. So this is the loop quantum. This is the loop quantum. First was the broad introduction of what is quantum gravity, then loop quantum gravity. And now I will turn to the last main part, which has to do with the one illustrative example. And that is a bridge between theory and observations in the cosmology of the early universe. So, in loop quantum gravity and the very early universe. For concreteness, I'm going to consider the inflationary paradigm. This paradigm has been highly successful, but it is not a fundamental theory. Like, for example, general relativity. In the classical regime, general relativity is a fundamental theory. But rather, as Jim Peebles likes to say, inflation serves as the framework on which to hang a fundamental theory. So that's what we're going to do. We're going to take the inflationary paradigm and try to construct a fundamental theory around it. And this fundamental theory is going to come from loop quantum gravity. So inflation begins much after the Planck regime, when matter density and curvature have decreased to about 10 to the minus 11 of the Planck density. In the Planck regime, matter density and curvature are Planck scale, and now they have fallen 100 billion times. That is when inflation begins, and that is why classical geometry can be used as an approximation here. And there is considerable work in loop quantum gravity to extend it to the Planck regime, and many, many people, I just named a few leading ones. And as I already mentioned, the Big Bang is tamed and is replaced by the Big Bounce. So what happens up here? So basically, here is a pictorial depiction of a universe. This is space, and this is time. Universe is expanding. So if you go back in time, you will find a Big Bang normally. But in loop quantum gravity, there is no Big Bang. The universe doesn't, the scale factor doesn't go to 0. It goes to the small finite value up here and then bounces back again. So basically, if you evolve back in time, there's a bounce and there is another universe. So if in forward in time, the universe which is contracting it comes to a small value of, then again bounces appear. So the Big Bang is replaced by a big bounce. And the Planck scale issues can be faced squarely. And this evolution has been studied by different groups, leading to a bridge between theory and observations. So here is an example of singularity. In the inflationary paradigm, I'm talking about Starobinsky potential, which is given up here. And it is considered very often because phenomenologically, it has been highly successful with the CMB observations of the Planck team. So here I'm plotting the inflaton, and here I'm plotting the volume of the universe. So inflation begins somewhere here, and the inflaton rolls down the potential, and it rolls down the potential, the volume of the universe increases, and it increases exponentially. If I go back in time, however, then using general relativity, you'll find that the inflaton actually has a turnaround. And then after the volume of the universe is if I go back in time, the volume of the universe is decreasing. And in general relativity, it will continue to decrease all the way in general relativity and become zero. And this will be the big bang up here. But in loop quantum gravity, what we have is that quantum mechanical effects start dominating and cause the universe to bounce here when the volume is still finite, the scale factor is still finite. What is behind this singularity resolution? Well, the key modification of Einstein's equation is well captured in quantum corrected Einstein's equations. So I could write down for you the full quantum mechanical Einstein's equation, the wave function of the scale factor and the scalar field and so on. But here, for our purposes, it will suffice to look at just some quantum corrected Einstein's equations. And leading order corrections already give you the bounds. And these corrections are, of course, coming from the quantum geometry. So, for example, the corrected Friedmann equation looks like that. The usual Friedmann equation is just the blue, A dot or A whole square is equal to 8 pi g times over 3. And using this equation, because this quantity is always positive, you can, and the matter density is always positive. Therefore, one can see that the universe A dot is either always increasing or always decreasing. You're always either in the contracting branch or you're in the expanding branch. But loop quantum gravity gives a correction 1 minus rho upon rho sup. And rho sup is a new constant, which is about 0.41 times rho Planck. And this is completely built, as I explained before, from the area gap. So area gap is what really makes this finite. If I send area gap to 0, this will become infinite. This term will disappear. So it is because we got a finite area gap, I got this term. And now what happens? Now when rho is equal to rho sup, 1 minus 1 becomes 0 and A dot can become 0. And therefore the universe can bounce. So the universe bounces when the matter density achieves the maximum sup is superior, so suprema. So my matter density approach gets the suprema. And the mechanism for this bounce is the following. We're not putting by hand any negative energy matter, any matters that violates the standard energy conditions, or we're not putting a new boundary condition which causes the universe to bounce. For example, like the Hartle-Hawking scenario, there is a new boundary condition. We're not putting a new boundary condition. Rather, quantum geometry itself creates a new unforeseen repulsive force in the Planck regime, and it overwhelms the classical attraction. If you like, this force is always there, but it is completely negligible compared to the classical attraction. But in the Planck regime, it dominates. And that is why the universe expands. And this has been understood in the Hamiltonian approach, or path integral approach, the consistent histories frameworks as well. And as I already said, the matter density has an absolute upper bound in the physical Hilbert space, and this upper bound is precisely this rho sup up here. And that provides a precise sense in which the singularity is resolved. Namely, matter density doesn't become infinite, it is bounded above. And as the quantum geometry effect is ignored, as the area gap is sent to 0, then this becomes infinite. So for students and people, beginning researchers, there's a short video which is called The New Meaning of Big Bang. It features Stephen Hawking, Roger Penrose, and 4 of us. And this was filmed quite independently. We did not know what the other people were saying in different geographic locations. And yet, surprisingly, we all say the same thing. And the main theme up here is that there is no physically a Big Bang. So I just want to emphasize that this is a mainstream consensus now, that there is no really physically Big Bang at which everything becomes singular. And this idea, I think in a detailed form, first came from loop quantum gravity. We had this loop big bounce up here. So this is a video that you might want to see. It's quite short. So now, okay, there is no Big Bang, there's a Big Bang bounce. But can it have any observable effects? I mean, how does it matter? Why does the pre-inflationary dynamics matter? Because inflation starts, so to say, in the beginning, in the middle, when the density is about 10 to the minus 12 times Planck density and evolves to the future. And now what we're saying is that if you go up to the past of this inflationary beginning of inflation, then our onset of inflation, when the so-called pivot mode exists the Hubble horizon. If I go to the past, you'll enter the Planck regime. Why does that matter? Well, first of all, people would say whatever happened in that Planck regime would be diluted away by inflation. But this is not true. Detailed examination many years ago already has shown that what happens is the following. If in fact the onset of inflation, there were some few excitations of geometry, the perturbations were not in a vacuum state, the Bunch-Davies vacuum state, but there were some excitations, then even if the universe expands out uniformly, these excitations don't get diluted away. Why? Because of stimulated emission that is, for example, used in laser. So because of stimulated emission, the density of this excitation remains the same. So there are more and more excitations, and therefore one can hope to see them in the observations. And now, how would one see them in the observation? So this is a cartoon on the left-hand side in general relativity. This is a very rough picture in which you got length scales here and time scales here. And what I'm plotting in red up here is the radius of curvature. So 1 upon square root of scalar curvature. That is what I'm plotting up here, radius of curvature. And scalar curvature blows up at the Big Bang, and therefore the radius of curvature goes to 0. And what I'm plotting in black up here are the evolution of wavelengths of various modes. And as the universe expands, the physical wavelength expands out here. At the Big Bang, all the wavelengths are 0. And what one finds is that all these expand out. But until at the onset of inflation, none of them actually have crossed the curvature radius. Now, why is the curvature radius so important? Well, the point is that if these excitations of the quantum field experience curvature, then they would actually get excited. If their wavelengths are smaller than the curvature radius, then they don't feel the curvature, they don't get excited. I mean, a simple example is that we know that Earth is curved, but the curvature radius is quite large compared to our human footstep. So when I walk on the Earth, I don't feel the curvature. But if I take a flight from here to Istanbul, for example, then I will feel the curvature. So if the wavelength is large enough, then it feels the curvature. And here the statement is that all the observable wavelengths in the CMB they don't feel the curvature until the onset of inflation. But here I got looped quantum cosmology. And here what happens is that the curvature doesn't blow up. Curvature at the bounds is finite, and therefore, curvature is finite, and therefore the curvature radius is not 0, but it's finite. And therefore it can happen that an observable mode actually actually feels the curvature. The wavelength up here is larger than the radius of curvature. So this mode can be excited. And then, as we saw during inflation, more and more of these excitations will be created. And therefore, at the onset of, as the universe expands, more and more of these excitations will be created. And at the onset of inflation, I will not be in the Bunch-Davies vacuum. So there is a very beautiful interplay between the ultraviolet and the infrared. It is the ultraviolet effects of quantum gravity that cure the singularity. That the curvature here is infinite in general relativity, is finite here. Radius of curvature is 0 here and is finite here. That is an infrared issue. But now when I look at primordial cosmological perturbations, this effect gets transferred to the longest wavelength modes That is to say, the infrared modes. And now the last question one can ask is, okay, these modes might get excited, but can they be relevant for observations? The answer is yes. In 2008, the Planck 2008 results paper, overview and cosmological legacy of Planck, it says, if anomalies have primordial origin, then their large-scale structures would suggest an explanation rooted in fundamental physics. It is worth exploring any models that might explain an anomaly, even better, multiple anomalies naturally or with few parameters. And the same thing was said here in the earlier version of Planck in 2015. So the question is, are there anomalies? If there are anomalies, they might have primordial origin and we might have signature of quantum gravity. So what are the cosmological CMB observations? And I think most of you know the CMB observation things. You have seen this plot many times. So by and large, it works very well, but at small wavelengths here, at large wavelengths, or small L's, these are the YLM L's, at small large angular scales or small L's up here, in fact, you can see that the actually observed power is lower than what is seen. So there is a power suppression. And this power suppression is really brought out most clearly in this picture up here, in this graph up here. So here is SA is a standard ansatz, which is inspired by inflation. So the red is a theoretical prediction, and here is the observation prediction. And especially from here on, you see that there's a big discrepancy between here. And what is one plotting is the angular correlation function in terms of theta. Here, one is plotting it in terms of YLMs. So it's really angle versus the YLM, spherical harmonic decomposition. And there is a second anomaly, which is called the lensing amplitude anomaly. From the observations, one can construct a quantity called lensing amplitude. Theoretical analysis assumes that the lensing amplitude is 1, but this value 1 lies outside the 68% confidence level of observations up here. And so there's an anomaly. So I just looked at two anomalies. There are other anomalies which have to do with spherical, hemispherical asymmetry and so on. So there are some small anomalies. And the point is that these anomalies might be pointers to physics beyond what we know, beyond the standard cosmological model. And what we propose is that, so this is again the statement up here. And what we are proposing is that they might be explained by quantum gravity effects. And this is indeed the case. The standard ansatz inspired by inflation assumes that the spectrum is of type some amplitude times the wave number upon a fiducial wave number, which is fixed by each mission times a parameter ns minus 1. If the ns is less than 1, this is negative, and therefore there is a slightly more power at smaller k's than at larger k's. And therefore, there's a red tilt. And inflation observations do say that this is just slightly less than 1. It's not exactly equal to 1. Exactly equal to 1 would be scale invariant power spectrum. And then the statement is that in loop quantum gravity, the power spectrum of primordial power spectrum of loop quantum gravity has a correction term f of k, which is equal to 1 for L bigger than 30, but for L less than 30, it is not equal to 1, and that is less than 1, and therefore there is actually power suppression up here. And you see clearly here in loop quantum gravity, the blue line, there is actually less power. And you can again go to this more precise measure, which is called the C theta measure up here. And as was emphasized in literature, this is somewhat better measure, and you can see that the anomaly is substantially reduced. There's a big improvement. There's a 2/3 reduction in this anomaly up here, and this quantity is called S1/2 because one is integrating from 60 degrees to 100 degrees, and this 1/2 just refers to the trigonometric function up here. So the anomaly. What about the anomaly in the lensing amplitude? Again, this is a little bit busy picture. The red ones up here, they refer to the standard ansatz. And in the standard ansatz, this was a picture up here, and 1 is outside the 68% confidence level. The blue is the one which is the loop quantum gravity prescription. And then one can see that it is squarely inside the 68% level. And therefore, this anomaly is also alleviated up here. And as a result, loop quantum gravity actually provides for you a slightly different 6-parameter lambda CDM model than the standard inflation. There are 6 parameters: the baryonic density, the cosmological constant, if you like. Then we got here the parameter which has to do with acoustic oscillations, parameter which is optical depth, how long the reionization epoch lasted, and then there is amplitude, the primordial amplitude, and the primordial NS, the spectral parameter, which tells you how the spectrum differs from the scaling variant spectrum. And most of these parameters agree they are very close to each other, within 0.5%, but the optical depth is increasing by almost 10% in loop quantum gravity. And therefore, new observations which are underway would actually check if this is correct or this is not. The change in the optical depth removed these anomalies, and therefore, if in fact these new values are actually confirmed, that would be a very good indication that quantum gravity effects do matter in the early universe. So let me summarize. Loop quantum gravity starts with a new syntax, namely quantum Riemannian geometry. And it uses it to address the long-standing conceptual issues of quantum gravity related to the absence of a sharp space-time geometry in the background, as well as the mathematical problems stemming from an infinite number of degrees of freedom of general relativity. By now, the basic framework has matured sufficiently to seek physically interesting applications. In general relativity, the most dramatic effects are associated with physical, dynamical nature of space-time in cosmology and black holes. This is already in the classical theory. At the onset of inflation, the curvature is about 10 to the 55 times the curvature at the horizon of a solar mass black hole. Most people don't realize that the curvature is so much stronger in the early universe than even near the horizons of black holes. That is why I use the early universe to illustrate the quantum gravity, loop quantum gravity implications. And the important thing was that there was a totally unexpected interplay between the ultraviolet and the infrared. Singularity resolution occurs because of the ultraviolet corrections to general relativity. And there's a new scale, however, that introduces the curvature radius at the bounds, which is 0 in classical theory, in general relativity, but it's finite here. And because it is finite, the wavelengths, which are larger than the curvature radius, they get excited and they change the physics, the cosmic microwave background physics at the largest observable scales, largest wavelengths or largest angular scales. And these effects alleviate 2 cosmologies and also lead to a prediction for future missions. Okay, let me just conclude with a final thought. For a very long time, or a century almost, loop quantum gravity has been really a domain of conceptual and mathematical research. And the problem has been with us for very long, because until recently, there was no obvious observational window to test the ideas. And therefore, leaders have made often appeals to aesthetics. And this is what I mentioned too early on in Young's quote. And also we saw that in cosmology. Until about 70s, 60s, 70s, people made an appeal to aesthetics and said that the steady state model, which is aesthetically more appealing and many leading cosmologists favored it for aesthetic reasons compared to the Big Bang model. But then observations show that Big Bang is correct. So aesthetics are okay because that's all we have in absence of observations, but they're far from being sufficient. But in quantum gravity, one finds quotes from eminent and thoughtful people like, it would have been a cruel God to have laid down such a pretty scheme and not have it mean something deep. Or this is in the context of so-called edge spaces and heavens of Newman and Blavatsky. I have too many nice things. I just think that too many nice things happen in string theory for it all to be wrong. Humans do not understand it very well. But I just don't believe that there is a big conspiracy that created this incredible theory that has nothing to do with the real world. I think these all, I mean, these are thoughtful people, but I think it is also important to keep in mind a reminder from Feynman. So I just rewritten the quotes on the last sentence. And what Feynman told us is the following. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are or what your name is. It doesn't agree with, if it doesn't agree with experiment, it's wrong. And we really should keep in mind when you're talking about quantum gravity. And there are many examples from history. I already mentioned steady state cosmology. Also, there was the idea that John Wheeler's that perhaps all the elementary particles will come out of geometry. The elementary particles are really excitations, geons, excitations of geometry. Then there was a replacement of quantum field theory by analytical properties of S matrix. These ideas are good, and maybe in future they might again be revived, but progress did not occur using these ideas. And at the end of in the end of 19th century, Lord Kelvin and Maxwell had this idea that atoms are really knots, are vortices in space. At that time, they believed in ether, so there were vortices in ether. And that again, that's how knot theory was born. So that really is a good mathematical theory, result. But physically, it doesn't mean anything. So we have to keep this in mind when you talk about quantum gravity. Okay, I want to end here. I just want to leave here a few references for students and postdocs who might be interested. Thank you very much.
Thank you so much for this very deep and exciting talk. So we can now pass to questions and have maybe some questions. Is it okay?
Yes, please.
Please ask questions or write your questions in the chat.
Yes. So one of the questions is there an analogy of Heisenberg uncertainty in quantum Riemannian geometry? Absolutely. The quantum Riemannian geometry is based on the Heisenberg uncertainty. And so the statement is that if I looked at, there is a Hilbert space of states and there are operators, and then there is uncertainty. So these Wilson lines, which are quantum excitations of geometry that I showed up here, these Wilson lines up here, these Wilson lines and the electric fluxes, so which give rise to area. These together, they don't commute with each other and they give rise to quantum uncertainties. And it is because of this really that we get rise to this discrete spectrum. I mean, as I said about the hydrogen atom, where I got this H hat, L squared, LZ, etc. Lx, Ly, Lz don't commute. They are discrete spectrum and so on and so forth. The same thing is happening in here. In fact, there's a close analogy between the L squared operator and between the area operator up here. So for example, areas, if I try to measure area of this surface and area of this surface, which intersect with each other, and if I have excitations which pass through these intersections, then these area operators would not commute on that state. So there is that deep, the Heisenberg uncertainty relations play a very deep role in all these things. The second question is, have I ever thought of quantum non-Riemannian geometry? Yes, in the sense of people are, for example, introduced torsion in here. People have, maybe that you think of as being Riemannian also. To begin with, the starting point was just this gauge theory without any background, right? So that gauge theory without any background, it has some excitations, it gives you some discrete geometry, and that is also something that is, it is not traditional. It's a manifold with various relations, various structures, various theorems. So you can think of it as geometry. And then, of course, there are these, non-Rajay geometries and that come up in spin forms. So people have thought about it. But as a question is implicitly implying that indeed the major focus has been on quantum Riemannian geometry. Yeah, there's a question here. Can we ask questions directly? I think that will be even easier, but let me just answer the next question, and then we can switch over to direct asking the questions. One of the questions is there a way to refute loop quantum gravity? How flexible is it? Can it be revised indefinitely? I think that's a great question. All quantum gravity theories are still in the infancy. So therefore, they're making, I mean, to my knowledge, actually, loop quantum gravity is the first one to make contact with cosmology, some direct contact with cosmology. So it could turn out, for example, that the predictions about this tau, the optical depth that was made up here, is actually falsified by experiments. That in fact, clearly the values predicted in loop quantum gravity lie outside 98-95% confidence level of actual measurements up here. That could well happen. Unfortunately, that would not be a refutation of loop quantum gravity as such, because in going from loop quantum gravity to loop quantum cosmology, a number of assumptions have to be made. Just like in inflation, you have to make some assumption about what is the initial state of the perturbations, what is the space-time geometry that you are looking at. So there are some assumptions about initial conditions there. So it will refute the initial conditions. The assumption of the initial conditions are wrong, and we have to go to the drawing board and actually look at the initial conditions better. It's only when experiments will be much, much more refined that one would be able to refute any quantum theory of gravity, including loop quantum gravity. There could be an inconsistency. In other words, there could be two predictions of loop quantum gravity which actually conflict each other. That could also happen, and that has not happened. But that's what, I mean, that would be an obvious refutation, but that has not happened. But I think the real refutation will come from experiments. And loop quantum gravity is making headway in that direction about making these predictions precisely to see if they can be falsified. The next question is there causal connection to the past of the big bounce of loop quantum gravity? And the answer is yes, in the sense that you could just, I did not really write down the equations which enable you to evolve the quantum state of geometry, the state psi, if you like, of the scale factor, anisotropies, the phi, and other things up here. So there is a state, and this state is evolved. You can evolve it from backward in time, you can evolve it forward in time. So in that sense, there is actually causality. You can also write down an approximate space-time. If you take your quantum state to be sharply peaked about a classical space-time, classical geometry. So let me just start from here, this picture up here. Supposing I start up here where the space-time geometry is very classical, and I consider a state which is very sharply peaked about this space-time geometry at this instant of time, and I can then evolve this state back in time up here. First remark is that this state actually remains sharply peaked, which is a surprise for us. I mean, it really is, and this has been checked with many, many different ways. Different methods, not just on computer, but various in the cosmological models, but various other tools up here. And then the statement is that you can actually evolve through the bounds, I should say, through the bounds on the other side, and get here a state which is again sharply peaked, and then if you go sufficiently far up here, then quantum gravity effects become negligible, just like here they were negligible, and then you can do everything with Einstein's general relativity. So past up here, to the past of here, you can do general relativity. To the future, you can general relativity, but here, the general relativity is drastically altered, and there is a quantum bridge between the past and the future. The next question is, it always seems to be assumed that gravity will have to be changed in the context of ultimate quantum gravity theory. What about changing quantum mechanics, in particular loop quantum gravity? Very good. So, of course, I mean, the statement is that to some extent, I mean, quantum gravity, quantum mechanics will also have to be changed, and I'll explain in a way. So it's not that one keeps one thing fixed but changes the other thing. So here, for example, that is why, in particularly when you apply to quantum cosmology, and then I'll also talk about something with quantum information in a second. So when you apply to quantum cosmology up here, then the statement is that, as we already saw, that we really cannot use this. There's no external measurement. There's no external apparatus. There's no external time. So Schrodinger equation, for example, I(h bar d by dt psi equal to h psi. There's no t. There's no external time. There's no space-time geometry. So of course, what we did was to look at generalized quantum mechanics by making it a quantum mechanics in which a relational quantum mechanics, in which one variable is treated as a clock. And there is a huge literature now. I mean, not huge, but very significant amount of literature on this using of relational quantum mechanics, using various clocks, how are the physical predictions related to each other, etc. And on the other side, there is a nice interchange between quantum information theory and quantum gravity people, and particularly people like Eugenio Bianchi and Ivan Aguirre are at the interface of this bridge. And the statement is that this bridge also sort of takes you beyond standard textbook quantum mechanics. Now, there are still Hilbert spaces of states, there are still operators, but the measurement theory or new aspects are really revealed up here, which are not revealed in ordinary classical theory. And also the measurement theory is different, because the universe as a whole the system is universal. It's an internal dynamics. It's a separation of a system and a subsystem. So that is what is happening. And finally, several years ago, I think it was in almost 20 years ago, 15 to 20 years ago, we had I had a paper, so you can look it up on the archives, which is called with Troy Schilling. He was my PhD student. And it is called, it's really generalization of quantum mechanics, exactly along the lines you're saying, namely, really going beyond the Hilbert space structure of quantum mechanics. And it was motivated by quantum gravity considerations, loop quantum gravity considerations, in which the Hilbert space structure itself is changed. And to me, it is really like it is the following. We got Minkowski space and we got general relativity, which is curved space-time. In Minkowski space, everything is flat. And now we got curvature. In flat space-time, we got many structures you can use using the flatness of space-time. They disappear in the curved space-time. So what we did was to, just like Minkowski formulated, Einstein's spatial relativity in a geometrical language, which then Einstein took to go to curved space-time. We took standard quantum mechanics and formulated in a geometrical language, which does not emphasize linearity so much, and then propose a few directions in which it could be generalized. And there's not been much progress. Almost 20 years have passed, but I think it's something that one might actually consider very, very seriously. Okay, next comment was, thank you very much. Okay, the question is, two questions. For a classical limit of loop quantum gravity, is the Einstein's gravity expected to be obtained directly as a limit, or some modifications of Einstein's gravity expected to be obtained depending on some energy scales? Very good. So the statement is that what people have done so far, especially the spin foam language, is really focused on just taking the drastic classical limit. And then the statement is that in the drastic limit, you do get just general relativity. But of course, you can just look at corrections to general relativity. But these corrections are going to have, for example, there is a parameter called the Barberi-Mirzi parameter, which is related to the area gap. I did not enter into it. It's a parameter of the theory. And so people might look at corrections. People are looking at corrections, which will depend on this parameter as well as with H bar. This is a subject which is still in flux. It is not settled enough. Okay, the second question is, to understand better, in quantum Riemannian geometry, is space-time an entity resolved, or does time become an emergent relational concept while space is quantized? So the statement is that in this picture of spin forms, really it's a covariant picture. It's a space-time picture. In the classical limit, you'll get space-time, not a wave function of spatial geometries. So in this picture, as you can see here, you've got two complexes. And these two complexes are really talking about space-time geometry. And then the happening is creation of these new nodes, for example, that is happening. And what one is calculating is really transition amplitudes to go from here to here. Now, in the simple cosmological models, we have been able to make contact between the Feynman path integral or the spin form picture in order to go from one instant of time to another instant of time, calculating these transition amplitudes and the evolution in relational time. But in full theory, this is not done. So the answer to your question is it's not that the space is quantized, but it's really a four-dimensional picture up here. And if you like, with respect to time, in the canonical picture, what is happening is that time is becoming a relational variable. In the spin form picture, what is happening is that you really have a two complex. So it's not that there is no, there's a two complex. And so therefore the happenings are really creation of new vortices, creation of new structures on these two complexes.
So thank you very much. Our speaker tied already too late. Perhaps we can stop here. But I want to ask final question. Okay. Is it okay?
Yeah, it's certainly okay. But other people, somebody said that they would like to ask the question on the not on the chat box, but so they might also want to ask first, and then you can ask the last question if you want.
Okay.
Does anybody else want to ask a question I don't know if they can ask it directly or not. Can you allow them to ask the questions directly? Or?
In principle, yes. Why not?
Okay.
So how can you comment Hawking information paradox resolution in context of loop quantum gravity? Perhaps you know recent works by this Success University group who discovered quantum here and states that the quantum here solve information.
I don't think they solve. They indicate something. This quantum here has to do with okay, so here is the black hole evaporation issue, right? And usually people, I'll be a little bit rapid. I hope that's okay. This is a space-time picture that people usually draw up here about you got a collapse that is happening and the black hole is collapsing and then the Hawking radiation is going out. But in the space-time picture, usually what people say is really that you got a final singularity and there is an event horizon. And then the black hole evaporates and it sort of just goes out here. So up in this future region up here, you've got flat space. This was the Hawking's original diagram. But I want to emphasize that this diagram was never derived from first principle. It was just a qualitative expectation. This has not been derived in any detailed sense up here. So one can just say what happens here. So one can look at semi-classical region. And really what happens is that there isn't an analog of the event horizon at all. What you have are these quasi-local horizons, which were introduced by many of us in the context of numerical relativity people, and they're used quite often and very frequently for numerical relativity people. So for example, if you have collapse like that, which is some thick null shell falling up, making a black hole, just like here, right? Here it was stellar collapse, but you could have a shell falling in and making a black hole. If a shell falling in and making a black hole, so there is a singularity. If it was just a classical theory, then I will have a picture like that. Okay, the shell fell in, make a black hole, and then this is the classical picture. But what happens up here is that as the shell falls in, there is a quasi-local horizon, which is not a black hole horizon that is formed. And then as the infalling matter stops, and then what's happening is that I just have outgoing matter, the Hawking radiation. And then this world tube of marginally trapped surfaces, which we call time-like dynamical horizon, that actually keeps shrinking. So this is shrinking as it is. And the radiation is going out up here. And now in loop quantum gravity picture, the statement is the following, that there really is no event horizon. So this picture in loop quantum gravity, which really is the source of a lot of questions and puzzles about it, is just incorrect. There is no singularity. Singularity is resolved. So the real picture is going to look something like this. I got a collapsing shell. I'm going to create a dynamical horizon, which grows in the classical region and shrinks in the quantum region. And then finally, it shrinks down to some Planck scale. And what happens here, we do not know exactly. But the point is that if I take a space-like surface like that, then the usual puzzle is that there are going to be, by the way, the hair that you talked about can be identified with multiple moments of this dynamical horizon. So this is something that is not that new. In the sense, it is new in this context of the Hawking evaporation. But this idea about this hair in terms of multiple moments is something that has been known for quite some time. So then the statement is that I got this hair up here and I got this radiation up here. But from loop quantum gravity perspective, the singularity is going to be resolved. So I'm not going to have a final singularity like that, but rather there's going to be some quantum region, which is in pink up here. And that quantum region in pink up here, then will become classical again. I mean, I got here again, you probably cannot see it. You again have so what happens is that in this region, everything is trapped. This is the boundary of the trapped region. This is the boundary of the anti-trapped region. And there is a transition surface separating the trapped region from the anti-trapped region. Okay, this is just for experts. But what happens is that there is no singularity. That's the main point. There is no singularity up here. And therefore, there is no event horizon either. So there is no singularity and there is no event horizon. You just have these dynamical horizons, but this is time-like. So things can come out up here. There's no problem. But at an early time, there will be correlations between here and what is inside the dynamical horizon in the black hole region up here, in the trapped region. But because there is no singularity, this information can just come out. So I can have a future region. And therefore, the correlations which seem to be lost in the early time are just restored at late times in loop quantum gravity. Now, this is not something that has been shown in all details. It should be, but that's what people are working on. This is the qualitative picture that we have in loop quantum gravity, and that is what various people are working to make precise.
Thank you so much. So last questions, please. Who wanted to ask directly questions, please?
Okay, that said that in the chat box, but I guess they no longer have questions, maybe.
So there is no questions. I don't see anyway. So if so, perhaps we can stop here. What do you think?
Yes, that's a good idea.
So thank you so much for this very nice talk, and we very much hope that to see you in person in our institute in the nearest future. So if you have final comments, please give, and then we will close the session.
I just wanted to say that, I got several Turkish friends from old time. Starting from Yavuz Nutku, who was a student several years ahead of me in Chicago. And then when I was a student, there was another student with me who was in particle physics, and we were both postdocs in Oxford, Cihan Saklioglu. Yeah, and then I also collaborated with a younger person, Ramazanoglu. And so, I got warm sort of relations with many Turkish physicists.
That's very nice. That's honor and pleasure.
Right. And the second thing is that, as I was mentioning before, I'm also interested in this, Yunus Emre's poetry, which I've been looking in translations. I was fortunately a Turkish colleague in my department. And so I can ask him for translations, and is this a good translation? Is this not a good translation? But I've been enjoying enormously the Yunus Emre poetry, and I'm very happy that there is the Culture Institute in honor of Yunus Emre now, which is like the analog in Germany for the Goethe Institute. So I'm very happy about that as well. So there's a non-physics interest in Turkey and Turkish civilization also. I mean, Yunus Emre in many ways was like Turkey. It's amazing. They were about the same. Well, Yunus Emre was much earlier than Goethe, but they both sort of contributed to the revival of the language and about the. So that's that's very, to me, that's and also that's the deep spiritual thoughts that are expressed in this poetry is very valuable to me.
So we can discuss all this when you will visit the Yunus Emre.
Okay. Okay. We can.
So we can close the session here.
Yeah, we can close the session.
Bye.